Welcome back. In today's video, we want to show that the power supplied to a resistive load cannot exceed V squared divided by 2 times Ri. Firstly, the circuit is an ideal battery or voltage source connected across a load resistor, RL. And in the circuit, in a circuit like this, we need to know what value will dissipate more power, because the question is, show that the power supplied to a resistive load cannot exceed this expression, which is V squared divided by 2 times Ri. So in order to find the power, so we're trying to show the maximum power condition, and we want to evaluate it with this guy to see if it can exceed this guy. So we know power is V times I. So we want to find the maximum current that this battery can produce. And then we want to find the load resistor that will promote or make the maximum power condition. So in order to do that, we can well, first let's just write down the current for this circuit. So that is I equals to V over RL, and the power is equal to V squared divided by RL. So now if we add our internal resistance, which makes up our battery, here we have our battery. So now our current for this circuit becomes V over Ri plus RL. So as we said earlier, we want to find the maximum condition. So I want to find at what value RL that there will be a maximum power condition. And as this guy goes to 0, we'll see that we have a maximum power condition. Less resistance, more current. Well, we'll see that we have a maximum current condition. So as RL goes to 0, we see that the current now becomes the terminal voltage of the battery divided by the internal resistance. So in other words, the internal resistance set the maximum output current of the battery. We can then look at the power delivered to the load or dissipated at the load. And then by looking at that expression, we can then find what value of RL will promote the maximum power condition. So we know that I is equal to the terminal voltage divided by the sum of the total resistance of the circuit, or the total resistance of the circuit. So then P is equal to I times V, or V times I, doesn't matter how you write it. And we know that I is equal to our following guy right there. However, though V, the voltage across the load, which is VL, is equal to the current through the resistor times the resistance of the load. So that would be I times RL. So that would be V times RL divided by RI plus RL. So then current becomes V squared. See, when we multiply these two expressions, we get V squared times RL divided by RI plus RL squared. So that would be RL. And we squared these, square that. And that gives us the power delivered to the load. So in order to, well, remember that when the load resistance goes to 0, so when this guy goes to 0, we see an increase in current. So less resistance, more current flow. So we see an increase in current. Well, we can find RL for which the power is maximized. So we can find RL that will promote the maximum power condition. And we can find that by taking the partial derivative of the power equation with respect to RL to find at what value of RL will produce this condition. So remember our true goal is to show that the power delivered to the load cannot exceed this guy. So we can take the partial derivative of P, and we're going to take that in terms of RL. I'm going to set that equal to 0, and then get our RL. So if we take the partial derivative, we know we take the partial derivative of the numerator times the denominator, these words. So that would be v squared times the denominator, which is Ri plus RL squared, and we minus that. So we know that this would be, if we expand the denominator, we know we get Ri squared plus 2 times Ri RL plus RL squared. We take the partial, if we take the derivative in terms, you can say partial derivative in terms of RL, we then get the following. So that would be 2 times RL. One moment. 2 times RL plus 2 times Ri. What's going on here? RL plus 2 times Ri. So that's the partial derivative of our denominator. And we multiply that by the numerator, which is v squared times RL, all over our denominator square. Oh, so that would be 4. Set that equal to 0. We can then go ahead and simplify this. So we get RL plus Ri squared minus 2 times RL plus Ri is equal to 0. If we rearrange, and we see that Ri is equal to RL. So you might want to just plug and evaluate the findings. Say, for instance, just plug this guy into the power equation. And let's do that for example. So if we plug that, so we know that Ri, what's going on with this guy? Ri is equal to RL, our power equation. We know that is equal to v squared times RL, Ri plus RL squared. We plug that in. We then get power is equal to v squared divided by 4 times Ri. And we see that is less than or equal to, well, got to be less than, it can't be equal to in this case, because one is going to decrease a lot faster than the other one, Ri. So the larger denominator produces less with every value of Ri. So we can put RL here as well. Well, the problem asked to show that cannot exceed. So in any sense, Ri is equal to RL, so it doesn't matter. And this shows that with every value of Ri or RL, this guy will decrease a lot faster. So therefore, this will never exceed this guy. So this is always greater than this guy. So this shows that the power dissipated at the load is at its maximum when the load resistance is matched to the source resistance. So this is what we have here. When the load resistance is matched with the source resistance, or the source internal resistance. Thus, a voltage source must have a low internal resistance compared to the load resistance. And if this is not true, then the voltage across the load will depend on the resistance of the load. And this is not ideal because we want the voltage source to dictate the voltage across the load, not the load resistance to dictate the voltage across itself. So that's it for today's problem, and I'll see you in the next one. Bye.